Thank you for joining our conference today. My name is Christopher Skack, and I am joining you today from the center of the Silicon Forest here in Beaverton, Oregon. I am glad to have the time to discuss this complex topic on creation and generation of radar signals with all of you. Radar has been part of our everyday life for many years, and Tektronix has been helping engineers and technicians develop and expand this technology ever since Tech was founded back in the 1940s. Today I will cover some of the basic terminology used in radar applications. Then I will talk about some of the challenges and solutions when creating and generating these signals. As I am presenting, please feel free to enter your questions, and I will make sure your questions are answered at the end of the presentation. Radar is actually a pretty basic technology of bouncing radio waves off of objects and looking at the reflections and determining size, distance, position, and speed. As this technology has improved, the basic concept has not changed, just the accuracy, resolution, and the many applications it is being used in. Military aerospace is still the main application area where radar is being used today, especially for long distances. As you can see in this slide, radar is critical for major defense applications and also used extensively for airport safety as well as weather information services. Short-range radar is used extensively for vehicles along highways. Specialized radar can also be used to provide imaging through fog, through walls, and underground. Here we see the main frequency bands that radar is used in. Today we will concentrate on the L through Ku bands, or from 1 GHz to 18 GHz frequency range. Automotive radar is also becoming a very popular application, but it is at a much higher frequency and deserves its own presentation that we may do at a later time. Radar systems can use continuous wave, or CW, signals, or pulse signals. The CW radar applications can be simple unmodulated Doppler speed sensing systems, such as police or sports-related radar systems, or may employ some type of modulation in order to sense range as well as speed. Modulated CW applications have many specialized in military applications. The range capability of CW radar systems is relatively short due to the RF and power requirements. Longer range radar systems are almost exclusively pulsed RF. The pulse duty cycle is usually well under 10%. The range and resolution are limited by the pulse repetition frequency, or PRF, as well as the pulse width and transmitted power. There is a trade-off between achieving good range and good resolution. For example, a wide or long pulse width leads to good range, but gives poor resolution for closely spaced targets. Narrow pulse width give good resolution but poor range. A technique called pulse compression is often used to overcome this fundamental trade-off. This slide illustrates the need for pulse compression to obtain good range and good resolution. Wider pulse widths have higher average power, which increases range. However, wide pulse width, i.e. long pulse durations, mean that echoes from closely spaced targets may overlap or run together in the receiver, appearing as a single target. Narrow pulse widths alleviate this problem, giving finer resolution and being able to separate closely spaced targets. Plus, compression techniques are often used to achieve good range and resolution. Pulse compression can be a confusing topic because it is a technique that allows the radar system to transmit wider pulses for good range while still achieving good resolution. It does this through the clever use of modulation of the RF signal during the pulse and using signal processing within the receiver to compress the detected pulses to narrow widths, thus achieving a good resolution. Pulse compression is achieved by employing different modulation techniques on the RF pulse and exploiting the modulation in the receiver to effectively narrow or compress the detected pulse width. The most common technique is to use linear frequency modulation, or LFM pulses. An LFM pulse is one where the pulse begins at one carrier frequency, then ramps linearly up or down until the pulse ends. LFM pulses are often called chirps or chirped pulses. Compression is achieved in the receiver by passing the signal through a match filter. This filter is designed to have a delay characteristic that is matched to the LFM frequency range and presents a delay to the signal that is proportional to the carrier frequency. For example, the filter may delay the starting frequency of the LFM more than the ending frequency of the LFM, thus causing the leading edge of the pulse to be delayed more than the trailing edge of the pulse. At the output of the filter, the pulse edges are close together in time, thus compressing the pulse width. Another common technique employs binary phase shift keying or BPSK modulation using a Barker-coded sequence. Barker codes are unique binary patterns that autocorrelate against themselves at only one location in time. The compression is achieved in the receiver, in this case by sensing the autocorrelation of the particular Barker sequence within the detected pulses. Other modulation techniques can be used as well, including stepped FM, stepped PM, nonlinear FM chirps, etc. As we'll see later on, arbitrary waveform generation techniques ideally suited for the creation and generation of these uniquely modulated and pulsed RF signals for test and characterization of modern radar and EW systems. Here we see some of the main pulse and envelope signal requirements, and in order to create these signals, all of these parameters need to be adjustable. As you can see, there are many variables that need to be adjusted. To do this with typical analog generator can be very challenging, and in many cases require many separate generators and many hours of configuration. So most systems today have much of the signal creation done digitally, and of course this also has its advantages and disadvantages. With the advance of high-speed digital to analog converters, or DACs, arbitrary waveform generators, or AWGs, have become the preferred method to perform complex radar testing. With an AWG, all the pulse parameters can be changed by just reprogramming the waveform memory. Most of the disadvantages are outweighed by the many advantages, and with the new AWG DAC technology such as higher resolution, faster sampling rates, and better memory management, some AWGs have a high power output option, or option AC, with a large amplitude range. Traditional generators are quickly being replaced with the state-of-the-art AWGs. AWGs have actually been included in many test systems for many years, so it is also important to be able to use previous techniques and signal waveform creation techniques with the newer state-of-the-art generators that provide more and more of the total test equipment required today. Electronic warfare applications present additional challenges for signal generation. Signal generation requirements include nearly everything discussed thus far in terms of complex modulation RF pulses for radar. EW applications have additional requirements for quickly changing or adapting the pulse RF signal modulation or other characteristics. These changes could be to spoof, jam, or deny proper operation of a detected radar system, an electronic attack or EA type activity, or to modify one's own radar system to adapt to a complex RF environment, an electronic protection EP activity. A common requirement for EW systems and system development is to be able to play back RF signals that have been observed or captured in the field. Again, AWGs are ideal tools to provide the flexibility to generate complex RF pulse trains that can respond to external stimuli, as well as being able to reproduce captured RF signals. In most EW systems, multiple emitters are also required in order to handle all of the many types of targets that need to be identified. AWGs are still the most versatile generators used for these systems, since AWGs can have independent channels and can also be synchronized so that multiple AWGs can be used to create these multiple emitters. Also, because of the higher resolution DACs that are available, it is possible to create a single waveform with many RF signals overlaid and output from one channel. As you can see from this list of requirements, programming AWGs can require many changing factors. The ability to generate signals with very low noise and clean, spurious, free dynamic range is critical. Many test scenarios also include being able to capture specific reflections from a dedicated receiver and store these signals that can be manipulated and played back to replicate specific situations. To simulate complex moving threats, the waveforms must be dynamically controlled by the test system, and new methods are being developed to make this easier. Because of all these variables, signal creation is not an easy task. Not only do you need to know the requirements of the radar poles being generated, but you also need to know the complexities of how the generator works and how to program the waveform memory correctly and efficiently. Since AWGs are FPGA and memory based, there are specific details of the hardware that need to be understood before the complex signals can be created. Most AWGs have a requirement for the number of memory samples that can be buffered from the FPGA to the actual DAC memory. This specification is usually called granularity. In order to handle memory efficiently, understanding this granularity spec is very important, and the lower this number is, the better. Basically, granularity is the buffer size that the total waveform length has to be divided by in order to be played out of the DAC. So even with a granularity, say, of 12 to 48, the waveform has to be created such that the total waveform memory length is divisible by this number. If it isn't, then either the waveform has to be trimmed or duplicated so that it does meet these requirements. Having a granularity of 1 or 2, which is in most of Tektronix AWGs, is the most desired, since this will be much easier to create the waveforms without wasting valuable memory. Other complexities include amplitude requirements and guaranteeing that the beginning of the waveform and the end of the waveform are matched. This is called the wraparound, such that when the waveform is repeated, there is no discontinuity that could cause spurs and phase mismatches. Other challenges are encountered when building sequences, which is basically a playlist of waveforms that can be accessed through an external trigger or dynamically while the sequence is playing. It is also important to know how the trigger system works, and when a trigger arrives, how long it propagates through the system and a waveform is played out of the actual analog channel, and how repeatable this is. For EW applications, it is also important to be able to add new waveform to the sequence table while another is playing. This basically provides an endless signal generation capability. Another capability that many systems require is the ability to capture and play back radar signals and other RF signals. Having this capability requires not only the ability to capture signals, but being able to accurately play those captured signals, or if necessary, RF carrier frequencies can be changed on the fly without having to recompile a new waveform. Even though AWGs are considered general purpose instruments, they dominate radar research and development as well as onboard active testing systems. Tektronix has been providing these instruments as well as developing easy-to-use software that improves overall efficiencies when performing these complex radar tests. Since AWGs have been used for this application for many years, it is also critical to have the backward compatibility so that previous setup and configurations can easily be modified to work with the newer state-of-the-art AWGs. One thing Tech has tried to do is make sure that if you have an old sequencer setup from an old AWG, it will work on the new AWG without too much pain. Tektronix has been developing waveform creation tools for AWGs for many years, and RF and radar waveform creation was one of the first applications developed. Since then, Tech has continued developing in these areas, with the main focus being ease of use and full-featured capability while maintaining full use of the advanced features of the hardware. Here we can see that recently released radar plugin that can run directly on a Tech AWG or run on your lab computer at your workstation. This methodology allows users to develop their specific signals away from the actual hardware, using the same software interface that is actually on the hardware. Here you can see the full-featured capability built into the radar plugin. This plugin takes into account all of the hardware considerations from the AWG as well as most specific radar pulse requirements. This plugin can be executed right from the AWG user interface or installed and run through the free remote application for your PC called Source Express. Source Express is a virtual AWG that uses the same user interface as the actual AWG hardware, so all waveform development can be done while the actual hardware is being used for testing. And then when the AWG hardware is available, the new waveforms can be drag and dropped onto the LAN connected instruments. The radar plugin also allows for antenna beam pattern settings to be applied. It allows some standard beam patterns and also custom beam patterns. This feature allows you to create waveforms to simulate losses as the radar antenna is being rotated. As you can see, this radar plugin provides all of the required flexibility to create the specific signals required and takes the pain out of you trying to do this through external programs like MATLAB or other similar packages, effectively making radar signals generation an easy task. With radar signals having to work in populated RF environments, many tests are required to make sure these competing RF signals do not impact the radar's accuracy. So building signals that have other radar or RF signal components has become a critical part of these complex radar tests. With the environment option, the radar software can include hundreds of these RF signals, all using different power and frequency settings. Here we see the interface in the software that enables building these complex multi-signal waveforms, and also the ability to add signals that have been captured using the real-time spectrum analyzer, or RSA. Today, this is an environment option for our RF Express software, but will be a separate plugin later this year that can be used with Source Express or directly through the AWG interface. The AWG Sequencer is probably one of the most used features when doing radar testing. This sequencer allows for very efficient memory management when outputting the signals, because radar signals are built from envelopes of pulses and dead times. Using the sequencer to break up the waveforms and repeat common parts allows for saving overall memory and increasing the playback time. Also, with sequence features such as pattern jumping, dynamic loading of waveforms, the sequencer can act much like a live streaming radar output and have the ability to change its output depending on feedback from the whole EW system. All hardware will have losses associated with it, such as cables, connectors, and components in the system. Also, the DAC in the AWG will have a sin x over x bandwidth roll-off due to the sample and hold characteristics of the DAC, and these need to be compensated in order to achieve a flat frequency response. Tech provides a pre-compensation plugin that allows users to compensate for these losses using a closed-loop system that creates a correction file that can be applied to the output waveform. As you can see in the images on the left, the non-corrected output, and then on the right is the corrected output. There is also the capability of using an S parameter file to compensate by using the inverse filter coefficient of the file and applying that to the waveform. Basically, either of these types of corrections just need to be applied to the waveform and then played out through the DAC output. Tektronix offers several AWGs for radar testing. The 70,000 series offers the best baseband performance with a frequency response up to 18 to 22 GHz, with its 10-bit resolution up to 50 gigasamples of DAC performance, it can provide a direct output up to the most common radar frequencies without the need for an up converter. With its sequencer and large memory capability, it is one of the most popular instruments used for radar testing today. Combine it with the radar plug-in and you have a system that enables the most efficient radar testing available. The AWG 70000 series also has an AC option, enables users higher amplitude and filtering capability that enhances this AWG for radar testing. This option provides the specific AC output that can be filtered and or amplified to provide the power needed for most radar applications. The AWG Sync Hub allows synchronization of up to 4 70000 series. So that's basically with a 2-channel box you can get 8 channels, or with the single channel box you can get 4 channels, enabling multiple emitter support. This option will automatically sync up the instruments with a minimal skew between channels, so no manual calibration is required, allowing for quick setup and test times. The latest AWG in the Tektronix portfolio is the AWG 5200 series. This AWG has a 16-bit DAC and up to 8 independent channels. It also provides the cleanest RF performance in its class with built-in AC and DC amplification. With up to 8 independent channels, you do not have to sacrifice resolution for channel count or amplification requirements. It also has 4 markers or digital outputs per channel. So for an 8-channel instrument, there are 32 digital outputs available. Reducing the size and cost for these radar and military systems is driving the evolution of modern DACs to integrate more functionalities into a single ASIC. Some of the more advanced high-speed DACs also incorporate digital signal processing and conditioning functionalities such as digital interpolation, complex modulation, and numeric controlled oscillators, or NCOs. This enables direct generation of complex RF signals in an efficient and compact way. The top figure shows a simplified block diagram from the high-speed 16-bit DAC used in each channel of the Tektronix AWG 5200 series, featuring digital complex modulator and multi-rate interpolation. With this internal IQ modulation feature, you remove the IQ mismatches that are attributed to external modulators and mixers. Also with this DAC, you can use several modes that enable you to output your signal at the cleanest portion of the DAC bandwidth and frequency roll-off positions. With its built-in interpolators, it also affords you the ability to create waveforms most efficiently, reducing waveform size, compilation times, as well as extending playback time. Here we can see the ability of the 5200 to produce very clean spurious-free outputs with this 4.25 GHz two-tone signal with max spurs at -70 dB. Tektronix has been providing radar analysis tools ever since we have been in business for over 70 years. So we know radar. And with the introduction of the new real-time spectrum analyzer, the RSA 7100 series, we now provide not only analysis up to 800 MHz bandwidth, but with real-time capture of up to 2 hours and full radar pulse parameter analysis. Also, Tektronix has tried to make analysis as easy as possible and maintain the same analysis software that has the same user interface for all the RF analysis products available, including the latest 70 GHz real-time scopes. So if you want to know radar, Tech knows radar, and we provide the best tools available to support all your needs in this very complex application environment.
Find out more at Vicom's website.